Okay, Assalamualaikum and salam sejahtera. Today in this video, I'm going to show you on how to solve the tutorial 2.2, which is related to transformer. Actually, in this topic 2, we have reached up to the transformer open circuit test and also short circuit test to determine the values of the components so that we can do the equivalent circuit of the transformer. Right, so we want to represent the actual transformer. For example, what we would like to represent it in terms of equivalent circuit. So what we do is to do the open circuit test and also the short circuit test. So we have the question, as you can see here, the equivalent circuit impedance of 20 kVA. This is the power of the transformer, 20 kilovolt ampere or kVA, and then 8,000 at the primary side of the voltage at the primary side, and then 240 voltage at the secondary side. 60 hertz is the frequency, and you don't have to worry about frequency. It doesn't change. All you need to use is the values of power, voltage at the primary and voltage at the secondary. Okay, so we want to determine what? We want to determine the impedances that we are going to use to write our equivalent circuit for this transformer. Okay, so from what we do is basically is we carry out the open circuit test and also the short circuit test to determine the values of voltage, current, and power at the during the open circuit, and also the voltage, current, and power during the short circuit test. So in the question, it has been given all of the information in terms of voltage at the open circuit, which is 8,000 volt, current at the open circuit, 7.133 ampere, and then power from the open circuit test, which is 400 watt. And then for the short circuit test, we also have been given with the values of voltage during the short circuit test, which is 489, and then current during short circuit test, which is 2.5 amperes, and then also power during the short circuit test, which is 240. So we're going to find the impedances, which is we can use this impedance to estimate our approximate equivalent circuit referred to primary side. This is what we are going to find in this question. All right, so basically I have done some initial sketch what is all about the tutorial 2.2 question, which is I have written here, which is this is the step down voltage actually, because we have 8,000 at the primary and then 240 at the secondary side. Okay, the power is 20 kVA of the transformer. All right, we have the values here from open circuit test and then also short circuit test values. So what we are going to determine is the components of equivalent circuit resistance, okay, series resistance, series reactance, okay, and then also the parallel branch, which is referred to the excitation impedances here, which is RC and also XM. Okay, so what we're going to do, which is because we have already got all of the values there, so now we start with firstly we have the voltage and at the primary and the voltage at the secondary. So what we do is to firstly determine its turns ratio, which is A equals to 8,000 divided by 240. So we got the turns ratio of 33.333. So this is the turns ratio which has no unit for the turns ratio. And then what we do is to find the power factor, okay, because we want to determine the theta, okay, for the angle okay, the angle of the impedances. So power factor can be determined by using PF equals to cosine theta, which is from the equation. We know that cosine theta is power of open circuit voltage, power of open circuit, okay, divided by voltage of open circuit times current of open circuit. So P equals to VI cosine theta, right? That is the equation that we have used to determine this theta. So basically we have all of the values of POC, VOC and IOC from the previous page. As you can see, we have the POC, IOC and VOC here. Then what we're going to do is just to determine the theta, just substitute of the values of POC, VOC and IOC. So we get cosine theta is POC is 400, VOC is 240, and current is 7.133. So finally we get the power factor, which is PF is 0.234. Let me just fix it 4, right? So we have the power factor. We know that the angle for the inductance based element is always lagging. All right, so this is power factor lagging. For the capacitor, it will be advancing, right? All right, the asset, then we're going to find the excitation admittance, which is YE. Okay, so we have done getting the power factor. We can use that power factor to find the YE, which is excitation admittance, given by IOC divided by VOC. Then this angle is already known. So negative here represents the negative here represents is lagging, lagging power factor. Cosine -1 of PF, which is we have PF here. Just substitute. So just to represent as PF first. Okay. So next is we just substitute all of the values that we have there, which is current divided by voltage, then angle negative cosine -1 of 0.234 as the one is this one, right? So further calculate this, we get 0.0297, angle of 76 -76.5 degree. All right, so that is the admittance. All right, so from admittance here in the form of polar, okay, so we can get the reactances, and also we can get the values of excitation branch here, excitation branch, because this is actually something like the something like this is YE, right? So we can further transfer this polar form to get the RC here and also XE, right? So what I'm gonna do is to transform this YE. Say I write it YE again, 0.0297, angle -79.5 degree. Okay, which is the same as the previous one. 76.5 actually. 297. Okay, it's correct. So we want to transfer this into the rectangular form. We can do the transformation as usual. So basically, I'm gonna skip this. Okay, change. I would like to write here. Transform from polar to rectangular. So once we transform it to rectangular form, we actually get another value of admittance 693 minus J 0.028888. So this is basically the conductance and susceptance. This is the conductance. This is the conductance. And this is the susceptance. All right. So actually, conductance and susceptance is inverse of the resistance and also inductance, right? Or reactance. Okay. So basically, this one is we can change this in the form of 1 over RC minus J 1 over XM. All right. So we know that 1 over RC is 0.00693. Okay, 1 over RC is 0.00693, and then 1 over XM is 0.02888, which is we can further find this XM and RC respectively. So just further calculate this. So we get RC is 1 over 0.0693. So just rearrange this these two. Okay, just rearrange that too, which is 144 ohm. And then XM similarly 1 over 0.02888, which is this one is 34.63 ohm. All right, so we get RC and XM as the parallel branch from the open circuit test. Okay, so we get admittance YE. Then from admittance, we can further calculate its conductance and also susceptance. Then from conductance and the susceptance, we can further calculate its resistance and also reactance. All right. So okay, so we have already found the parallel branch. So we already got the parallel branch from the open circuit test, which is this one is 0.0693, right? So this one is J. Sorry, I'm gonna use this one. RC is 144, okay, and XM is 34.63. Okay, so we have got that already. Now, from the short circuit test, we are going to determine another values, which is the series components. Okay, so we have so firstly we have the values of short circuit test here. The first thing first, we are going to find the power factor during the short circuit test. So power factor during the short circuit test is, which is PF equals to, use the same equation, which is now we use the values of short circuit. Okay, short circuit values PSC divided by VSC ISC. Okay, then from here PSC is 240, VSC is 489, and ISC is 2.5 ampere. Then we get value of the power factor 0.196, which is this is also lagging power factor. Then once we get the power factor, we can just determine the values of the series impedances ZE. So series impedances consists of equivalent resistance and also equivalent reactance, right? So ZSE, now we can calculate it by using VSC divided by ISC, which is angle we have already determined, angle of the power factor. Okay, so now just substitute all of the values that we have. 489 of voltage divided by 2.5 of current, and then cosine, right? Then we can further convert this, and then this one is 195.6. Then angle 78.7 degree. Okay, so angle 78.7 degree. This one negative 76. So okay, so let me just check it for a while. Okay, let me just check it. All right. So from here, polar form of this ZE, okay, now we can just convert this into rectangular form. All right, so we can just convert this into rectangular form. Let me just so it will just something tricky here, as you can see. Okay, previously when we calculate the power factor, we put on negative. Okay, this is for admittance. Okay, this is for admittance because this one we are going to convert it into 1 over RC and 1 over XM. Basically for this one, it is actually for this one it is actually 1 over, this is actually plus 1 over JXM. Okay, for the calculation you have to be careful of that. So this is actually 1 over JXM, but since we want to put J at the denominator, okay, so it becomes negative. Okay, it becomes negative J 1 over XM. Right, so just be careful. So that is why this is the series one. So series one, no problem, because we just make sure that this is a series. We know that this must be positive. Okay, so let's convert this to polar form. I'm just black color. All right, the series impedance, this one we want to convert to rectangular form. I just keep the way how we convert polar to rectangular because you have learned it before. So this one becomes 38.4. This is J192. Okay, so this is actually REQ, equivalent resistance, and the other one is XEQ. Okay, so this is series branch, not parallel branch. That is why plus J, right? So finally, top search results. So finally, we resketch the equivalent circuit. I'm going to resketch the equivalent circuit first before I write down all of the values that I've got from my calculation. Okay, so this is resistance, equivalent resistance, then reactance over there. So we have values. This is REQ, JXEQ, and then this one is IS over A as usual. This is IP. Okay, the current coming in, the current out, and this side is VP. All right, and then the other side is AVS. So what we're going to represent here, all of the impedances. Okay, right, so this one is RC, and the other one, this is JXM. Okay, so this is the impedances referred to the equivalent circuit. This equivalent circuit is approximate equivalent circuit refer to primary side. So if you refer to the equivalent circuit referred to the primary side, okay, the parallel branch, which is this, the parallel branch, which is RC and JXM here, okay, can be determined by using the turns ratio. All right, we have the from ZSE just now. So from ZSE, we have REQ. Sorry, this one we have already got. Okay, no problem. This is already, we already got from our calculation. This one, okay, just use another color. So this is RC, this is XM for the secondary. This is also for the secondary. Okay, now we are going to convert this to the impedances referred to primary side, okay, the high voltage side. This is step down. So we're going to use this RC primary is A square RC secondary, which is this one is, we know that A is 33.3333 this is square, and this RC is this one. RC as this one is XMS. CS is 144 ohms. This is 159 kilo ohm. So then XM primary referred to primary side, which is A square XMS then we get 38.4 kilo ohm. So we have 159 for RC, and then 38.4 for kilo ohm for the XM. Okay, so we just can write down all of the values that we get from our calculation. Okay, so REQ is 38.4, XEQ is 192. This one is 192, 38.4. Okay, then RC is 159, XM is 38.4. Okay, so kilo ohm, this is kilo ohm. Just make sure that write the symbol as well, because it will not confuse. All right, so okay, just finish calculating all of those values. Okay, so that's all for the equivalent circuit that we have got from the values given in terms of open circuit test and short circuit test of the transformer. Then we can further calculate the admittance from the open circuit test, and then also, sorry, not admittance, yes, admittance, excitation branch. This one we can use to further calculate the series branch, series admittance and impedance. Okay, series impedances, not admittance, series R and X EQ. Okay, then we can further draw our equivalent circuit that referring to the primary side, which is the high voltage side. Okay, using the turns ratio. Okay, using turns ratio, then we got all of the values. Then we just represent in terms of equivalent circuit. I think that's all for the explanation about example 2.2, which is also tutorial 2.2 of this part. Okay, so I think that's all. Okay, thanks.